Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable. Let your body settle wherever you are. Adjust your pillow. There's no rush. We have all the time we need. Where in the world are you watching from? A quiet room as the evening deepens? Perhaps a cozy corner where the day is finally winding down? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something remarkable and unexpected. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, looked deeper into space than we've ever looked before, and what it found has shaken our understanding of the universe's beginning. Galaxies that shouldn't exist, stars that formed too early, black holes that appeared impossibly soon after the Big Bang. The cosmic timeline we thought we understood is being questioned. But don't worry, this isn't going to be an overwhelming flood of crisis and confusion. Instead, we'll move slowly and carefully through one of the most exciting discoveries in astronomy, learning what Webb saw, why it surprised scientists, and what it might mean for our understanding of how the universe began. By the end, I think you'll find a deep appreciation for how science works, how discoveries challenge our knowledge, and how the universe continues to surprise us. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds. So settle in, let your shoulders drop, take a slow, deep breath, and let it out even more slowly. And let's begin our slow drift through the deepest observations ever made, through images that have changed how we think about the universe's first moments. There's nowhere you need to be. Just listen and let the story unfold. Let your thoughts wander among the ancient galaxies that Webb has revealed. Let's start with the telescope itself, because understanding what the James Webb Space Telescope is and where it operates helps us appreciate what it has discovered. Webb is not orbiting Earth like the Hubble Space Telescope. It's much farther away, in a very special location. Webb orbits the Sun at a point called the second Lagrange point, or L2, about 1 million miles from Earth. This is a location where the gravitational pulls of the Sun and Earth balance in just the right way that a spacecraft can stay there with minimal fuel, orbiting along with Earth as our planet circles the Sun. Why so far from Earth? Because Webb observes in infrared light, wavelengths longer than visible light that we perceive as heat. To see faint infrared signals from distant galaxies, Webb itself must be extremely cold. If it were close to Earth, our planet's warmth would overwhelm the faint signals Webb is trying to detect. At L2, Webb can position its giant sunshield to block light and heat from the Sun, Earth, and Moon all at once, keeping its instruments at about minus 230 degrees Celsius. The telescope is massive, much larger than Hubble. Its primary mirror is 6.5 meters across, composed of 18 hexagonal segments made of beryllium and coated with gold. Gold is used because it reflects infrared light exceptionally well. The mirror segments can be adjusted individually, allowing the telescope to focus with extraordinary precision. Behind the mirror are 4 scientific instruments, each designed to capture different aspects of infrared light. The near-infrared camera, or NIRCAM, takes the stunning images we've seen in the news. The near-infrared spectrograph breaks light into spectra to determine what objects are made of. The mid-infrared instrument observes at even longer wavelengths, and the near-infrared imager and slitless spectrograph specializes in detecting faint objects. Getting Webb to L2 was an incredible achievement. The telescope launched on Christmas Day, 2021, folded up inside a rocket because it was too large to fit in the rocket's nose cone fully deployed. Over the following weeks, as it travelled to L2, Webb unfolded like origami, deploying its sunshield, extending its mirror segments, and calibrating its instruments. Engineers on Earth watched nervously as each deployment step occurred, knowing that if anything went wrong, the telescope was too far away to repair. Unlike Hubble, which astronauts visited multiple times to fix and upgrade, Webb is beyond human reach. Everything had to work perfectly the first time. Scientists had predictions for what Webb would see when it looked that far back. They expected to find small, primitive galaxies, the first structures forming from the primordial gas left over from the Big Bang. They expected these early galaxies to be dim, containing only young stars, lacking the heavy elements that form in later generations of stars. What Webb actually found was different, very different. And that difference is what we're going to explore together. The telescope sits out there now, 1,000,000 miles away, orbiting the Sun in sync with Earth, its golden mirror collecting ancient light, its instruments measuring photons that have travelled across most of the universe's history to reach it. It's humanity's time machine, our way of seeing the cosmic past, and what it has shown us has raised more questions than it has answered. The universe's early history, it turns out, was more complex, more active, more surprising than we imagined. Our models predicted cosmic infancy. Webb showed us cosmic maturity. The timeline is being questioned, and scientists are working to understand what it means. This is the story of those discoveries, told slowly and carefully with patience and wonder. Let's explore what Webb found in the deep universe and why it matters. To understand what Webb discovered, we need to understand how looking at distant objects means looking back in time. This concept is crucial, and once you grasp it, the rest of the story becomes clearer. Light travels at a finite speed, about 300,000 kilometers per second, or 186,000 miles per second. This is the fastest speed possible in the universe. Nothing can go faster than light. But even at this incredible speed, light takes time to cross cosmic distances. But there's a complication. As the universe expands, space itself stretches. This stretching affects the light travelling through it. Light waves get stretched too, shifting toward longer wavelengths. This is called redshift, and it's crucial for understanding Webb's discoveries. When a galaxy is very distant, its light has been travelling through expanding space for billions of years. The expansion has stretched the light significantly. Visible light emitted by that galaxy has been stretched into infrared wavelengths by the time it reaches us. The farther away the galaxy, the more its light has been stretched, and the more redshifted it is. This is why Webb observes in infrared. The most distant galaxies, those from the earliest times, have their light shifted so far into the infrared that visible light telescopes like Hubble can barely detect them. Webb, with its infrared sensitivity and large mirror, can see these ancient, extremely redshifted galaxies clearly. Astronomers measure redshift using the letter Z. A redshift of Z equals 1 means the light's wavelength has been doubled by the universe's expansion. A redshift of Z equals 10 means the wavelength has increased by a factor of 11. The highest redshifts correspond to the earliest times. Hubble's deepest images showed galaxies with redshifts up to about Z equals 11, corresponding to times about 400 million years after the Big Bang. Webb has found galaxies with redshifts beyond Z equals 13, possibly as high as Z equals 16 or even 20, corresponding to times as early as 200 million years after the Big Bang, maybe earlier. These numbers might seem abstract, but they represent an incredible achievement. Webb is showing us the universe in its infancy, in its first few percent of its current age. It's like looking at baby pictures of the cosmos, seeing the first structures forming, the first galaxies assembling, and here's where the surprise comes in. Those baby pictures don't show what we expected. Instead of small, primitive, struggling galaxies, Webb is showing us galaxies that look surprisingly mature, surprisingly massive, surprisingly well organised. It's as if we expected to see infants, and instead found teenagers. This discrepancy between expectation and observation is what has shocked astronomers. The timeline doesn't quite work. The universe shouldn't have had enough time to form such galaxies so early. Yet there they are in Webb's images, undeniable and puzzling. How did these galaxies form so quickly? How did they accumulate so much mass? How did they develop such organised structures? These are the questions scientists are grappling with, and the answers might require us to rethink some fundamental assumptions about how the universe evolved. But we're getting ahead of ourselves. Let's take this slowly, building up the full picture piece by piece, understanding both what we expected and what Webb actually found. Before Webb launched, astronomers had a clear picture of what the early universe should look like, based on decades of theory and observation. Understanding these expectations helps us appreciate why Webb's discoveries are so surprising. The standard model of cosmology, the framework scientists use to understand the universe's history, goes something like this. The universe began in the Big Bang about 13.8 billion years ago. Initially, it was incredibly hot and dense, filled with a soup of fundamental particles. As it expanded and cooled, those particles combined to form the first atoms, mostly hydrogen and helium with traces of lithium. For about 380,000 years, the universe was opaque, filled with ionized plasma that scattered light. Then, as it cooled further, electrons combined with atomic nuclei, making the universe transparent for the first time. This is the moment we see in the cosmic microwave background, the faint glow of ancient light that fills the sky. After that, the universe entered what's called the Dark Ages. It was filled with neutral hydrogen gas, no stars yet, no galaxies, just diffuse gas slowly collapsing under its own gravity into denser clumps. Dark matter, the invisible substance that makes up most of the universe's mass, played a crucial role, its gravity attracting ordinary matter into the first structures. The first stars formed perhaps 100 to 200 million years after the Big Bang, igniting in the densest regions of gas. These were not stars like our Sun. They were likely much more massive, hundreds of times the Sun's mass, burning brilliantly but briefly, living only a few million years before exploding as supernovae. These first stars, called population 3 stars, had a crucial job. They produced the first heavy elements heavier than helium. When they exploded, they scattered these elements into space, enriching the gas from which the next generation of stars would form. Gradually, over hundreds of millions of years, the first galaxies assembled. According to the standard model, these early galaxies should be small, perhaps containing only a few million stars, compared to the hundreds of billions in modern galaxies like the Milky Way. They should be irregular in shape, lacking the organized spiral or elliptical structures we see in nearby galaxies. These early galaxies would merge, colliding and combining to form progressively larger galaxies. Galaxy formation was expected to be hierarchical, building from small to large over billions of years. By the time the universe was a few billion years old, large galaxies like the Milky Way should have formed. The rate of star formation should also evolve. Early on, with lots of available gas, star formation should ramp up. The universe's peak era of star formation was expected around 2 to 3 billion years after the Big Bang. Before that, in the first billion years, star formation should be significant but not yet at its peak. Supermassive black holes, the million to billion solar mass monsters found at the centres of most large galaxies, should also form gradually. Small black holes from the first stars would merge, accumulating mass over time. The very largest black holes, billions of times the Sun's mass, should take billions of years to grow. This was the picture, a universe that starts simple and slowly becomes complex. Small structures form first, then merge into larger ones. Star formation ramps up gradually. Black holes grow through slow accretion and mergers. The first few 100 million years should show the earliest, most primitive stages of this process. Detailed simulations run on supercomputers showed what early galaxy formation should look like. Gas cooling and condensing, dark matter halos pulling in material, stars igniting in the densest regions, small galaxies merging. The simulations predicted certain numbers of galaxies at different times, certain sizes and brightnesses, certain star formation rates. These predictions were not wild guesses. They were based on well-tested physics, on our understanding of gravity, gas dynamics, star formation, and dark matter. The models had successfully explained many other observations. There was good reason to trust them, so when Webb turned its gaze to the deepest universe, astronomers expected confirmation. They expected to see the model validated, to watch the earlier stages of galaxy formation unfold as predicted. They expected dim, small, primitive galaxies struggling into existence in the cosmic dark ages. That's not what they found, and the discrepancy between prediction and observation is what makes this discovery so compelling, so challenging, and ultimately so exciting. The universe, it seems, had other plans. When NASA released Webb's first deep-field image in July 2022, the astronomical community and the public alike were stunned. The image showed a small patch of sky, about the size of a grain of sand held at arm's length, filled with thousands of galaxies. The target was a galaxy cluster called SMACS 0723, about 4.6 billion light-years away. The cluster itself is interesting, but it wasn't the main attraction. Instead, astronomers used the cluster as a natural telescope. Massive galaxy clusters bend space due to their enormous gravity, creating a gravitational lensing effect. Light from more distant galaxies behind the cluster gets bent and magnified as it passes through the cluster's gravitational field. This allows us to see faint, distant galaxies that would otherwise be too dim to detect. In Webb's image, the cluster galaxies appear as bright yellowish elliptical galaxies in the foreground, but scattered throughout the image are thousands of more distant galaxies, appearing as smaller, redder, sometimes distorted arcs and smudges. Some of these are among the most distant galaxies ever observed. What struck astronomers immediately was the clarity. Structures in these distant galaxies billions of light-years away, were visible in exquisite detail. Spiral arms, bars, bright knots of star formation, all could be seen with unprecedented sharpness. Webb's large mirror and infrared sensitivity were revealing the distant universe in a completely new way. But as astronomers analysed the image more carefully, they began to notice something unexpected. Some of the distant galaxies that should be from the universe's early epochs, looked surprisingly bright. They looked surprisingly large. They looked surprisingly well-formed. Spectroscopic follow-up, where Webb splits the light from these galaxies into spectra to measure their exact distances, confirmed that some were indeed from very early times. Galaxies at redshifts of Z equals 7, 8, 9, and even higher were appearing in the data. And they weren't all small and dim. Some were quite massive, containing billions of stars. Some showed evidence of organised structure, suggesting they weren't just chaotic clouds of gas and young stars, but had already formed some internal order. This was the first hint that something was different, that the early universe might be more complex than the models predicted. But it was just one image, one field of view. More observations were needed. Over the following months, Webb conducted additional deep surveys. The Cosmic Evolution Early Release Science Survey observed several fields, building up statistics on early galaxies. The Glass and Sear surveys targeted specific regions known to contain high redshift galaxies from previous Hubble observations. As data accumulated, the pattern became clearer. The early universe, seen through Webb's eyes, was busier than expected. There were more galaxies at high redshifts than models predicted. These galaxies were on average brighter, more massive, more structured than anticipated. Of course, distance estimates from images alone can be uncertain. A galaxy might appear redder and dimmer because it's very distant, or because it's covered in dust, or because it contains only old stars. Spectroscopy is needed to be certain. Webb began spectroscopic observations of the most interesting candidates. In many cases, the spectra confirmed the high redshifts. The galaxies really were from the early universe, and their properties, measured from the spectra, often confirmed that they were indeed more massive and more chemically enriched than expected. Not every candidate held up. Some objects that appeared to be extremely distant galaxies turned out to be closer dusty galaxies, or even foreground stars. This is normal in astronomy. Preliminary identifications are always subject to revision with better data. But enough candidates were confirmed that a clear picture emerged. The early universe contained a population of surprisingly mature galaxies. Not all galaxies were like this. Many small, dim, primitive galaxies were also found as expected. But the massive, bright ones were more common than predicted. This wasn't a case of one or two weird outliers. It was a systematic excess, a population of objects that shouldn't be there in such numbers, at least not according to our models. Something was different about the early universe, and scientists needed to figure out what. The images themselves are beautiful, even without understanding the science. Galaxies of all shapes and colours scattered across the black background of space, some nearby and bright, others distant and faint, each one an island of billions of stars. Each with its own history. Webb has given us a new view of the cosmos, deeper and clearer than ever before. But beyond the beauty is the puzzle. What are we really seeing in these images? What do they tell us about how galaxies form, how the universe evolved, how structure emerged from the primordial chaos? These questions are what drive scientists to analyse every detail, to measure every galaxy, to test every model. Let's focus on specific examples, because understanding particular galaxies helps make the abstract concrete. Several galaxies observed by Webb have become famous among astronomers for their unexpected properties. One example is a galaxy given the catalogue name GLASS Z13. Observed as part of the GLASS survey, this galaxy appeared to have a redshift around Z equals 13, placing it about 300 million years after the Big Bang. If confirmed, it would be one of the earliest galaxies ever observed. But what surprised astronomers wasn't just the distance, it was the galaxy's brightness and apparent mass. From the data, scientists estimated it contained perhaps 1 billion stars. 1 billion stars formed in just 300 million years, from a universe that started with no stars at all. To put this in perspective, imagine compressing all of the Milky Way's star formation history, billions of years of stellar birth, into just 300 million years. You'd need an incredibly high star formation rate, far higher than we observe in most nearby galaxies. Moreover, forming stars requires gas, and that gas needs to cool and collapse. These processes take time. 300 million years seems barely enough for even one generation of stars to form, let alone enough generations to build up 1 billion stars and the heavy elements that stars create. Another example is a galaxy candidate called Maisie's Galaxy, named after the daughter of one of the astronomers who first identified it. This galaxy was estimated at redshift Z equals 14, about 280 million years after the Big Bang. Spectroscopic follow-up suggested the redshift might be somewhat lower, around Z equals 11, but that's still remarkably early. What's interesting about Maisie's Galaxy is its brightness in certain wavelengths, suggesting active star formation. It appears to be undergoing a burst of star formation, creating stars at a high rate. Again, this is surprising for such an early time. Where did all the gas come from? How did it collapse so quickly? Then there are galaxies showing evidence of heavy elements. Stars produce elements heavier than helium, carbon, oxygen, nitrogen, iron, through nuclear fusion in their cores and in supernova explosions. The first stars contained almost no heavy elements, only primordial hydrogen and helium. But some of Webb's early galaxies show spectral signatures of heavy elements, indicating that multiple generations of stars have already lived and died, enriching the gas with their nucleosynthesis products. This suggests these galaxies have been forming stars for a while, maybe hundreds of millions of years. But if they've been forming stars for hundreds of millions of years by the time we observe them at, say, 400 million years after the Big Bang, then they must have started when the universe was very young indeed, perhaps just 100 million years old. That pushes star formation back to times when the universe was supposed to still be in the Dark Ages. There are also observations of surprisingly mature morphologies. Some early galaxies show hints of structure, disk-like shapes or central bulges, suggesting they've had time to dynamically relax and organize themselves. But that organizational process should take time, perhaps billions of years, not just a few hundred million. Not all of Webb's early galaxies are surprising. Many are small, dim, irregular, just as predicted. The models aren't completely wrong, but the models didn't predict the abundance of massive, bright-structured galaxies that Webb is finding. That's the discrepancy. Astronomers have coined phrases to describe this situation. They talk about early galaxies, or, although that last phrase is a bit sensational, the galaxies exist, so they're not truly impossible, but they're unexpected. The existence of these galaxies doesn't mean our entire understanding is wrong. It means our models need refinement. The basic picture of the Big Bang, cosmic expansion, structure formation, all of that remains well established. But the details of how galaxies form in the first billion years, those details are being questioned and revised. This is how science works. Models make predictions. Observations test those predictions. When observations don't match predictions, scientists investigate. Sometimes the observations are wrong, sometimes the models are wrong. Often it's more subtle, with both needing refinement. In this case, the observations are quite solid. Webb is a reliable instrument, and the data has been carefully analysed. The galaxies are real, so attention turns to the models. What might we be getting wrong? What physics might we be missing? What assumptions might need revisiting? These are the questions astronomers are actively working on, publishing papers, holding conferences, running new simulations. The field is alive with activity, energized by the discrepancy between what we expected and what Webb has shown us. And beyond the specific scientific questions is a deeper truth. The universe is still teaching us, still showing us things we didn't anticipate. Despite centuries of astronomy, despite powerful telescopes and sophisticated theories, nature still has the capacity to surprise us. If surprising galaxies weren't enough, Webb has also found something even more puzzling. Supermassive black holes in the early universe, far earlier than they should exist. Let's explore this mystery. Supermassive black holes are the giants lurking at the centres of most large galaxies, including our own Milky Way. They contain millions to billions of times the Sun's mass, concentrated in regions smaller than our solar system. Their gravity is so strong that nothing, not even light, can escape if it gets too close. Hubble had already found some early black holes, quasars at redshifts around Z equals 7, about 700 million years after the Big Bang. These black holes contained hundreds of millions of solar masses, surprisingly massive for their time but not completely inexplicable. Perhaps they grew slightly faster than the Eddington limit allows, or perhaps they started from unusually massive seeds. Webb has now found black holes at even earlier times, and some are even more massive. One example is a quasar detected at redshift Z equals 10.1, about 450 million years after the Big Bang. The black hole powering this quasar is estimated at several hundred million solar masses. 450 million years might sound like a long time, but it's not nearly enough to grow a black hole from stellar seeds to hundreds of millions of solar masses, even at the maximum growth rate. The math doesn't work. There are several possible explanations. One is that the initial seeds were much larger than expected. Instead of forming from individual massive stars, creating black holes of perhaps 100 solar masses, maybe the first black holes formed through direct collapse of massive gas clouds, creating seeds of 10,000 or even 100,000 solar masses. This direct collapse scenario requires special conditions. The gas cloud must collapse without fragmenting into stars, which normally happens when gas cools and condenses. If the gas can be kept warm enough to resist fragmentation but still collapse under its own gravity, it might form a massive black hole directly. Another possibility is that the Eddington limit doesn't strictly apply in the early universe. Maybe black holes could accrete faster than the theoretical limit, through mechanisms we don't fully understand. Perhaps turbulence or magnetic fields or some other process allows more rapid growth. Or maybe the black hole masses are being overestimated. The mass estimates come from observing the black hole's effects on surrounding gas and stars. If those models are wrong, the inferred masses might be too high, but Webb is finding not just one or two early black holes, but a population of them. Multiple quasars at redshifts beyond Z equals 8 have been detected. This suggests that whatever process forms supermassive black holes was quite efficient in the early universe. More efficient than current models predict. There's also the question of how black holes and galaxies grow together. In the nearby universe, there's a tight correlation between the mass of a galaxy's central black hole and the mass of the galaxy's bulge, the central concentration of stars. This suggests that black holes and galaxies co-evolve, influencing each other's growth. But in the early universe, some of Webb's observations suggest that black holes might be growing faster than their host galaxies. Some early quasars appear to have black holes that are unusually massive compared to their host galaxies, violating the expected correlation. This could mean that black holes form first and then help trigger galaxy formation around them, rather than forming later within already assembled galaxies. Or it could mean that the early correlation was different, evolving over time to the tight relationship we see today. Understanding these early black holes is crucial because they affect their surroundings. When supermassive black holes accrete matter, they release enormous amounts of energy, more energy than all the stars in the galaxy combined. This energy can heat gas, drive powerful winds, and even shut down star formation in the galaxy. So black holes aren't just passive objects sitting at galactic centres. They're active players in galaxy evolution, influencing when and where stars form, how gas flows through galaxies, how galaxies merge and interact. Getting black hole formation wrong means getting galaxy evolution wrong too. The early black holes Webb has found are forcing astronomers to reconsider how these cosmic giants form and grow. The models that worked for the nearby universe might not apply to the earliest epochs. New physics, new processes, new pathways to black hole formation might be needed. This is another piece of the puzzle, another surprise from Webb's deep observations. The early universe was not only forming massive galaxies faster than expected, it was also forming massive black holes faster than expected. Both findings point toward a more active, more energetic, more rapid period of structure formation than standard models predicted. To understand why Webb's discoveries are so challenging, we need to talk about dark matter, the invisible substance that plays a crucial role in galaxy formation. Dark matter might hold part of the answer to the puzzles Webb has revealed. Dark matter makes up about 85% of the matter in the universe. It doesn't emit, absorb, or reflect light, so we can't see it directly. We know it exists through its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters are more massive than their visible stars and gas suggest, and gravitational lensing reveals invisible mass-bending light. What dark matter is remains one of physics' great mysteries. The leading hypothesis is that it consists of exotic particles, perhaps WIMPs, weakly interacting massive particles, or axions, that interact with ordinary matter only through gravity. Despite decades of searching, these particles haven't been directly detected. But even without knowing what dark matter is, we understand how it behaves gravitationally. It clumps together under its own gravity, forming halos, vast clouds of dark matter that serve as the gravitational scaffolding for galaxies. In the early universe, dark matter began collapsing into halos before ordinary matter did. Dark matter could clump freely, unimpeded by radiation pressure or gas pressure, while ordinary matter remained too hot and diffuse to collapse. These dark matter halos then attracted ordinary matter. Hydrogen and helium gas fell into the halo's gravitational wells, where it could cool and eventually form stars. Galaxies formed inside dark matter halos, with the halo's mass determining how much ordinary matter could be accumulated. There are several possible explanations. One is that star formation in early galaxies was more efficient than we thought. Normally, only a fraction of a dark matter halo's mass is converted into stars. Most of the ordinary matter remains as gas, either not falling into the halo or falling in but not forming stars. The efficiency of this conversion depends on many factors: how quickly gas can cool, how effectively supernova explosions blow gas out of galaxies, how black holes affect their surroundings. Maybe in the early universe, conditions were such that star formation was more efficient, converting a larger fraction of available gas into stars. Another possibility involves the dark matter itself. Most models assume dark matter is cold, meaning the particles move slowly compared to the speed of light. Cold dark matter clumps readily, forming halos at all scales. But if dark matter is warm, meaning the particles move faster, it resists clumping on small scales. Warm dark matter would allow large halos to form but suppress small halos. This might affect the early universe's structure formation in ways that could reconcile Webb's observations with theory. Alternatively, dark matter might interact with itself more than we think. Most models assume dark matter particles only interact through gravity, but if they have weak self-interactions, it could affect how halos form and evolve. Self-interacting dark matter might create different halo structures, potentially affecting galaxy formation. These ideas are speculative. Cold dark matter remains the best supported model, successfully explaining most observations. But Webb's findings are causing some astronomers to reconsider, to ask whether dark matter's properties might need slight adjustments to match the data. There's also the question of dark matter halo assembly. Simulations suggest halos grow through smooth accretion of smaller halos, a gradual process. But maybe early halos grew faster than simulations predict, through different mechanisms or under different conditions in the very young universe. Understanding the interplay between dark matter and galaxy formation is crucial. Dark matter provides the gravitational potential wells, but ordinary matter forms the stars we see. Getting the dark matter right is necessary for understanding why galaxies look the way they do. Webb's observations are essentially telling us that either our dark matter models need refinement, or our understanding of how ordinary matter behaves in dark matter, halos, needs updating, or possibly both. This isn't a crisis that invalidates dark matter theory. Dark matter remains well established from many independent lines of evidence, but the details of how it drives galaxy formation might need adjustment, particularly for the earliest epochs where conditions were different from today. Dark matter is the invisible choreographer of cosmic structure, guiding where and when galaxies form. Webb is showing us that the dance in the early universe might have been different from what we choreographed in our models. Understanding why will deepen our knowledge of both dark matter and galaxy formation. The first stars in the universe, those that formed from purely primordial gas with no heavy elements, play a crucial role in the story of early galaxies. Webb's findings are causing scientists to reconsider when and how these first stars formed. These first stars, called Population 3 stars, have never been directly observed. They should have all died billions of years ago, as massive stars live only millions of years before exploding. But their influence shaped the universe that followed, and understanding them is key to understanding early galaxy formation. Population 3 stars are predicted to have been very different from modern stars. With no heavy elements to help cool the gas, the collapsing clouds that formed them remained hotter than clouds forming stars today. Hot gas resists fragmentation, so instead of forming many small stars, primordial clouds likely formed individual very massive stars. These stars might have been dozens or even hundreds of times more massive than the Sun. At such masses, they would burn incredibly hot and bright, with surface temperatures over 100,000 degrees. They would emit copious ultraviolet radiation, ionizing the hydrogen gas around them. Because they were so massive, they lived fast and died young, perhaps lasting only a few million years before exhausting their nuclear fuel and exploding as supernovae. These explosions would scatter the first heavy elements into space, enriching the gas from which the next generation of stars would form. The timing of when these first stars formed is uncertain. Models suggest they could have formed as early as 50 to 100 million years after the Big Bang, once dark matter halos became dense enough to allow gas to collapse. But the uncertainty is large. They might have formed earlier or later. Webb was partly designed to find these first stars, or at least their signatures. Astronomers hope to detect population 3 star formation in the earliest galaxies, seeing the characteristic spectrum of pure hydrogen and helium with no heavy elements. So far, Webb hasn't definitively detected population 3 stars. This isn't too surprising. Individual stars are too faint to see at such distances. We can only observe galaxies, collections of millions or billions of stars. Detecting the signature of a few population 3 stars among millions of later generation stars is extremely difficult. But the absence of a clear population 3 signature and the presence of heavy elements in some early galaxies suggests that by the time Webb observes these galaxies, at say 300 to 400 million years after the Big Bang, they've already gone through multiple generations of star formation. This implies population 3 stars must have formed significantly earlier, perhaps at 100 to 200 million years after the Big Bang or even sooner. Otherwise, there wouldn't have been time for multiple stellar generations by the time Webb sees these galaxies. Some models are now proposing that population 3 star formation was more widespread and occurred earlier than previously thought. Maybe the first dark matter halos assembled faster than simulations predict, allowing star formation to begin sooner. Or maybe population 3 stars formed in bursts, with many forming quickly in the first dense halos, their supernovae enriching large volumes of gas rapidly. This could accelerate the transition from primordial to metal-enriched star formation. There's also reconsideration of how efficiently population 3 stars formed. Standard models assume a certain star formation efficiency, but maybe it was higher in the early universe. More efficient star formation would mean more stars formed from available gas, creating more supernova enrichment and faster evolution toward later generation stars. Another question involves how population 3 stars affected their environment. Their intense ultraviolet radiation would ionize surrounding gas, creating bubbles of ionized hydrogen that might affect subsequent star formation. Their supernova explosions would inject energy and momentum, possibly triggering or suppressing further star formation. The reionization of the universe, when radiation from the first stars ionized all the hydrogen that had recombined after the Big Bang, is another piece of the puzzle. Observations suggest reionization was largely complete by about 1 billion years after the Big Bang. But it probably started earlier. If population 3 stars were abundant and formed early, they would contribute significantly to reionization. Their ultraviolet radiation would ionize large volumes of space. Understanding when and how reionization occurred constrains when the first stars formed. Webb is observing this reionization process indirectly by looking at how light from distant quasars is absorbed by intervening hydrogen. As reionization progresses, less neutral hydrogen remains to absorb light. By measuring absorption at different distances, astronomers can track reionization timeline. Early results from Webb suggest reionization might have been more complex than simple models predicted, with some regions ionizing earlier than others, creating a patchy structure rather than a uniform progression. This complexity could reflect varied population 3 star formation across different regions. All of this feeds back into the question of early galaxies. If population 3 stars formed earlier and more efficiently than thought, they would create the conditions for subsequent galaxy formation to proceed faster. More heavy elements would be available sooner, allowing for more efficient cooling and star formation. This could help explain why Webb sees mature galaxies earlier than expected. The first stars are the foundations upon which everything else was built. Getting their story right is essential for understanding the galaxies that followed. Webb's observations are forcing a re-evaluation of this foundational epoch, suggesting it was a more active and dynamic period than we realized. Computer simulations play a crucial role in modern cosmology. allowing scientists to test theories by creating virtual universes and comparing them to observations. Webb's findings have revealed discrepancies between simulations and reality that are driving new research. Cosmological simulations start with the early universe shortly after the Big Bang. They encode the laws of physics: gravity, gas dynamics, star formation, supernova feedback, black hole growth. Then they evolve the universe forward in time, watching as structure forms, galaxies assemble, stars ignite. The most sophisticated simulations include billions of particles representing dark matter and gas, following their interactions over billions of years of cosmic time. They reproduce the large-scale structure of the universe, the distribution of galaxies, the properties of galaxy clusters, often with impressive accuracy. By increasing star formation efficiency in the early universe, simulations can produce brighter, more massive galaxies at early times. But there are limits. Too high an efficiency creates other problems, producing too many stars in later galaxies, conflicting with observations of the nearby universe. Another approach involves adjusting feedback mechanisms. Supernova explosions inject energy into galaxies, heating gas and sometimes ejecting it into intergalactic space. The strength and effectiveness of this feedback affects how many stars form. Weaker feedback in the early universe could allow more star formation, creating brighter galaxies. Black hole feedback is also being reconsidered. Active black holes can heat and expel gas, regulating star formation. But if early black holes were less effective at this, or if they hadn't yet grown large enough, feedback would be weaker, again allowing more star formation. Some researchers are exploring variations in dark matter properties. Simulations usually assume cold dark matter with no self-interactions, but if dark matter is slightly warm or self-interacting, it could affect halo formation and thus galaxy formation. Others are considering whether the initial conditions might have been different. Simulations start from the density fluctuations measured in the cosmic microwave background. But if those fluctuations had different properties on small scales than we assumed, it could affect early structure formation. There's also scrutiny of how simulations implement physics at subgrid scales. Simulations can't resolve individual stars or small gas clouds. They average over these small scales using approximate recipes. If those recipes are wrong, the simulations might not accurately predict early galaxy formation. Testing simulations requires comparing many properties, not just galaxy numbers and brightness. Simulations predict galaxy sizes, shapes, colors, star formation rates, chemical abundances. Webb measures all these properties, providing stringent tests. Early comparisons suggest that no single adjustment fixes all the discrepancies. Increasing star formation efficiency helps with some properties, but worsens others. The situation is complex, likely requiring multiple refinements to match observations. This process is how science progresses. Simulations encode our understanding of physics. When they don't match observations, either the observations are wrong, or the physics is incomplete, or the implementation is flawed. Careful analysis determines which. In this case, the observations are robust. Webb is a well-understood instrument, and multiple independent teams reach similar conclusions. So attention focuses on the simulations. What are we getting wrong? What physics might we be missing? Some possibilities are mundane. Maybe we underestimated star formation efficiency, or got feedback strengths wrong. Others are more profound. Maybe we don't fully understand dark matter, or maybe there's new physics affecting the early universe. The good news is that this process improves simulations. Each discrepancy identified leads to improvements, refining the models, deepening understanding. The next generation of simulations will incorporate lessons learned from Webb, making better predictions that future telescopes can test. There's also humility in recognizing that simulations are approximations. They can't include every piece of physics, can't resolve every scale. They make simplifying assumptions, use approximate recipes, trade accuracy for computational speed. They're powerful tools but not perfect predictors. Webb is teaching us where our simulations succeed and where they fail, which provides invaluable guidance for improving them. The goal is convergence, simulations that match observations across a wide range of properties, giving confidence that we understand the underlying physics. We're not there yet for the early universe. Webb has revealed our current simulations fall short, but that's exciting, not discouraging. It means there's new physics to discover, new processes to understand, new insights waiting to be uncovered. Given all these surprises from Webb, a natural question arises. Could our entire understanding of the Big Bang and cosmic history be wrong? Let's address this carefully and honestly. The short answer is no. The Big Bang theory as a whole is not wrong. The evidence supporting it is overwhelming and comes from multiple independent sources. But the details, particularly about the first billion years, are being refined, and that's what Webb is helping us do. Let's review the evidence for the Big Bang. First, the universe is expanding. Galaxies are moving away from each other, with more distant galaxies receding faster. This expansion was discovered by Edwin Hubble in the 1920s and has been confirmed by countless observations since. If the universe is expanding, then in the past it was smaller and denser. Run the expansion backward, and you reach a time when the universe was incredibly hot and dense. That's the Big Bang. Second, the cosmic microwave background radiation exists. This is the faint glow of light from about 380,000 years after the Big Bang, when the universe first became transparent. It fills the sky uniformly, with a temperature of about 2.7 degrees above absolute zero. The CMB has been measured with extraordinary precision by satellites like COBE, WMAP, and Planck. Its properties match Big Bang predictions perfectly. Its temperature, its spectrum, its tiny fluctuations all agree with theoretical calculations. Third, the abundances of light elements match Big Bang nucleosynthesis predictions. In the first few minutes after the Big Bang, nuclear reactions created hydrogen, helium, and traces of lithium and beryllium. The predicted ratios of these elements match observations of the oldest stars and gas clouds, a precise confirmation of Big Bang physics. Fourth, the evolution of the universe matches predictions. Galaxies at greater distances, earlier times, look different from nearby galaxies, showing evolution over cosmic time. The universe's large-scale structure, the distribution of galaxies and galaxy clusters, matches predictions from Big Bang-based models. These lines of evidence and others establish the Big Bang framework beyond reasonable doubt. The universe began in a hot, dense state about 13.8 billion years ago and has been expanding and cooling ever since. What Webb is questioning is not the Big Bang itself, but the details of what happened in the first billion years. How quickly did structures form? How efficiently did stars form? How did the first galaxies assemble? These are important questions, but they're details within the Big Bang framework, not challenges to the framework itself. Some sensational headlines have suggested Webb disproves the Big Bang. This is not accurate. Webb's observations are unexpected within current galaxy formation models, but they don't contradict the fundamental Big Bang evidence. There are modifications being considered. Perhaps the universe expanded slightly differently than we thought in its earliest moments, affecting structure formation. Perhaps dark matter properties are subtly different. Perhaps star formation efficiency varied with time in ways we didn't anticipate. These are refinements, not replacements. It's like finding that a recipe needs adjusting, but the basic cooking method is sound. We're tweaking ingredients and temperatures, not discarding the whole recipe. There are also more radical ideas being proposed. A few scientists suggest alternative cosmological models that might better explain Webb's observations. These models typically modify aspects of the Big Bang theory, perhaps changing how gravity works on cosmic scales, or how the universe expanded in its early moments. These alternatives face significant challenges. They must explain not just Webb's observations, but all the other evidence that supports the standard Big Bang model. So far, none have succeeded in doing so as comprehensively as the Standard Model, even with its current puzzles about early galaxies. Science is self-correcting. When observations don't match predictions, theories are modified or replaced. But replacement requires a better alternative, one that explains both the new observations and all the old ones. Until such an alternative exists, the Standard Model remains the best framework, even as we work to resolve its current puzzles. It's also worth noting that being surprised by observations is not failure, it's progress. Science advances by discovering things that don't fit current understanding. Those surprises drive research, leading to deeper understanding. This is the nature of scientific knowledge. It's never complete, never final. Each generation builds on the previous one, refining, improving, occasionally revolutionizing. Webb is giving us the next step in understanding the universe's earliest chapters. So no, we're not wrong about the Big Bang, but we're learning that the story is richer, more nuanced, more surprising than we realized. And that's wonderful. It means the universe still has secrets to reveal, still has the capacity to astonish us. Let's pause and reflect on what Webb's discoveries tell us about how science works, because this is science at its best, responding to unexpected observations with curiosity and rigor. Science is not a collection of unchanging facts. It's a process, a method for understanding the world through observation, hypothesis, and testing. Scientists develop theories that explain existing observations and make predictions about new ones. When new observations confirm predictions, confidence in the theory grows. When they don't, the theory must be re-evaluated. Webb's observations are an example of the second case. The standard galaxy formation models predicted certain properties for early galaxies. Webb's observations showed different properties. This doesn't mean science has failed, it means science is working. The response from the astronomical community has been exactly what it should be: intense scrutiny of both the observations and the theories. Multiple teams are analysing Webb's data independently, checking for errors or biases. Others are revisiting galaxy formation models, identifying assumptions that might need revision. Papers are being published at a rapid rate, each examining different aspects of the puzzle. Some focus on improving distance measurements, ensuring the galaxies really are as distant as they appear. Others model star formation processes, testing whether changes in efficiency or feedback can explain the observations. There's healthy debate, scientists proposing different explanations, testing them against data, refining ideas through peer review and discussion. This is how scientific knowledge advances, through the collective effort of many researchers examining evidence from multiple angles. Importantly, the debate is focused on refining details within a well-established framework, not on questioning the basics. The Big Bang, cosmic expansion, dark matter, these foundational concepts remain secure, supported by multiple lines of evidence beyond what Webb is observing. What's being questioned is how galaxies form in the first billion years, what determines star formation efficiency, how black holes grow, how feedback processes operate. These are important questions, but they're second-order details, not first principles. This distinction is crucial. Popular media sometimes portrays scientific revisions as crises or failures, suggesting scientists don't know what they're doing. But revision is a strength, not a weakness. A scientific theory that never needs updating probably isn't making predictions daring enough to test. Consider the history of cosmology. A century ago, we didn't know the universe was expanding. The Big Bang theory didn't exist. Galaxies were thought to be nebulae within our Milky Way. Our understanding has transformed completely. That transformation came through observations that challenged prevailing ideas. Hubble's discovery of cosmic expansion, the detection of the cosmic microwave background, the measurement of light element abundances. Each observation forced revisions, building toward our current understanding. Webb is continuing that tradition. It's not overturning everything we know, but it's revealing complexities we didn't anticipate. The first billion years of cosmic history is more nuanced than our models captured. That's a discovery, not a failure. There's also recognition of uncertainty. When scientists say they're puzzled by Webb's observations, they're being honest about the limits of current knowledge. Science doesn't claim to have all answers, it claims to have a method for finding answers. That honesty sometimes gets misinterpreted. When a scientist says quote 4 or quote 5, it doesn't mean all of science is wrong. It means this particular phenomenon needs more study. The process playing out now, analysing Webb's data, proposing explanations, testing them against additional observations, this is science functioning properly. It's messy and sometimes slow, but it's effective. Eventually consensus will emerge on which modifications to galaxy formation theory best explain the data. There's also excitement in the community. Unexpected observations are opportunities. They push scientists to think creatively, to question assumptions, to develop new ideas. Many astronomers are energized by Webb's findings, eager to solve the puzzles. This excitement is what drives people to become scientists. Not the comfort of knowing all answers, but the challenge of finding new ones. The universe poses questions, and scientists work to answer them. Webb has posed some excellent questions. Another aspect is the collaborative nature of modern science. Webb itself is a product of collaboration. Thousands of engineers and scientists from multiple countries working together over decades. The data analysis involves researchers worldwide sharing techniques and results. The scientific process ensures that errors are corrected, biases are identified, and understanding improves over time. Not quickly perhaps, and not without mistakes along the way, but steadily and reliably. Webb's observations will be integrated into our understanding through this process. Years from now, textbooks will incorporate what we've learned from Webb. The story of early galaxies will be richer, more accurate, informed by these observations. Future students will learn the refined version, building on the work being done now. That's the nature of scientific progress. Each generation stands on the shoulders of the previous one, seeing a little farther, understanding a little more deeply. Webb is helping us see farther into cosmic history than ever before, and our understanding will grow accordingly. Webb's discoveries have raised questions that will take years to fully answer. Let's think about what happens next, how astronomers will follow up on these findings, and what future observations might reveal. First, more observations are needed. Webb has observed relatively small areas of sky in great detail. To understand whether the surprising early galaxies are common or rare, larger surveys covering more sky are necessary. Several large programs are planned or underway to do exactly this. These surveys will find more early galaxies, improving statistics. With larger samples, astronomers can better characterize the population, their typical masses, brightnesses, star formation rates, chemical compositions. This statistical information will constrain models more tightly than individual galaxy measurements can. Spectroscopic follow-up is also crucial. Many early galaxy candidates have distances estimated from images alone, which can be uncertain. Spectroscopy provides precise redshifts and detailed information about the galaxy's properties. What stars they contain, how fast they're forming stars, what elements are present. Webb has limited time, with many teams competing for observations. Prioritizing which galaxies to observe spectroscopically is a challenge. The brightest and most interesting candidates typically get priority, but this creates a bias toward unusual objects. Ground-based telescopes are also contributing. New extremely large telescopes, like the Extremely Large Telescope in Chile, will complement Webb with different capabilities. They can observe large numbers of galaxies more quickly, providing statistical samples that Webb's detailed observations can then contextualize. Theoretical work will advance in parallel. New simulations incorporating lessons from Webb will be run, testing whether specific modifications to galaxy formation models can reproduce the observations. These simulations will make new predictions that future observations can test. There will also be attempts to understand individual galaxies in detail. For particularly interesting objects, astronomers will use Webb to study their structures, map their star formation, measure their kinematics, how they're rotating or moving internally. These deep dives can reveal formation processes. Multi-wavelength observations combining Webb's infrared data with radio, submillimeter or X-ray observations will provide complementary information. Different wavelengths trace different physical processes. Radio reveals cold gas, submillimeter shows dust emission. X-rays indicate hot gas or active black holes. As more data accumulates, patterns should emerge. Are massive early galaxies clustered together, suggesting they formed in special environments? Do they show signatures of recent mergers? Are they systematically different from smaller early galaxies in ways that models can explain? There's also the possibility of direct detection of population 3 stars. While difficult, careful searches might find galaxies or regions within galaxies showing the signature of primordial composition stars. This would directly constrain when and how the first stars formed. Measurements of reionization will continue. Webb can observe how neutral hydrogen at different distances absorbs background light, tracking how reionization progressed. This provides independent information about early star formation, since stars drove reionization. Looking farther ahead, future space telescopes will build on Webb's discoveries. Concepts exist for even larger infrared telescopes, or for telescopes optimized for specific wavelengths. These might not launch for a decade or more, but they'll continue pushing our view deeper into cosmic time. There's also hope for detecting the very first stars through different methods. For instance, if population 3 stars created black holes that later became seeds for supermassive black holes, gravitational wave observations of black hole mergers might provide indirect evidence. The Laser Interferometer Space Antenna, or LISA, planned for the 2030s, will detect gravitational waves from massive black hole mergers. If some of these black holes trace back to population 3 stars, their merger rates and masses might reveal information about the first stellar generation. Closer to the present, astronomers are already proposing new observing programs for Webb, building on initial discoveries. Some focus on following up specific galaxies in more detail. Others plan to survey new regions of sky, searching for rare extreme objects. There will be surprises along the way. Webb might find even earlier galaxies. Pushing the timeline back further, it might detect phenomena we haven't anticipated. Each surprise will generate new questions and new research directions. The timeline for resolving current puzzles is uncertain. Some questions might be answered within a few years as data accumulates. Others might take a decade or more, requiring new theoretical insights or additional observations beyond Webb's capabilities. But this is normal in science. Major discoveries often raise more questions than they answer initially. The full implications take time to understand. Webb's observations of early galaxies will likely occupy astronomers for years to come. The puzzles Webb has revealed will eventually be solved. Modifications to galaxy formation theory will converge on explanations that match observations. New simulations will reproduce Webb's findings. The timeline of early cosmic history will be refined, but in solving these puzzles, we'll undoubtedly raise new ones. That's the nature of frontier science. Each answer opens new questions. The universe is deep and complex, and we're still in the early stages of understanding it. Webb is giving us the tools to explore that depth, to push our knowledge farther, to understand the cosmos more completely. What an extraordinary time to be studying the universe, to witness discoveries that challenge and expand what we thought we knew. Behind every observation, every analysis, every model are people. Let's take a moment to appreciate the human side of Webb's discoveries, the scientists whose work has revealed the early universe. The James Webb Space Telescope itself represents decades of human effort. First proposed in the mid-1990s, it took over 25 years from concept to launch. Thousands of engineers, scientists, technicians and administrators contributed. Many people dedicated their entire careers to Webb, working on it for 20 or 30 years. Some retired before it launched, never seeing their work come to fruition. Others saw it through from beginning to end, experiencing both setbacks and triumphs. The technical challenges were immense, building a mirror that could unfold in space, creating instruments that could work at temperatures just above absolute zero, designing a sunshield the size of a tennis court that had to deploy perfectly, all required innovations and years of problem solving. There were delays and budget overruns. Webb was originally supposed to launch in 2007 with a budget of $1 billion. It finally launched in 2021 with costs exceeding $10 billion. These delays and costs generated criticism and scrutiny. But the teams persevered. They solved each technical problem, passed each review, met each requirement. The fact that Webb worked perfectly from day one, that everything deployed correctly, that it exceeded performance specifications, is a testament to their dedication and skill. Now, astronomers worldwide are using Webb, analysing its data, making discoveries. These are the scientists who proposed the observations, who wrote the software to process the data, who spent long hours ensuring every detail was correct. There's also a generational aspect. The astronomers analysing Webb's data today include those who helped plan the telescope decades ago, now senior in their careers, and younger scientists who were children when Webb was being built, bringing fresh perspectives and energy. There's also communication with the public. Scientists give talks, write articles, participate in documentaries and podcasts, sharing their discoveries. This outreach is important for maintaining public support for science funding, but it also carries responsibility to communicate accurately. The media sometimes sensationalizes findings, using headlines like "quote 6" when the reality is more nuanced. Scientists then face the challenge of correcting misconceptions while still conveying the genuine excitement of discovery. Some scientists are more comfortable with public communication than others. Not everyone who excels at research also excels at outreach. But increasingly, scientific training includes communication skills, recognizing that explaining one's work is part of the responsibility. There are also personal stories behind the discoveries. Scientists choosing to work on Webb data while balancing family responsibilities, caring for children or aging parents. International collaborations bringing together people from different cultures and backgrounds. Friendships forming through shared scientific interests. And there are sacrifices. Long hours at the expense of personal time. Career uncertainty for early career researchers facing competitive job markets. The stress of funding pressure, constantly writing proposals to support one's research. But there's also joy. The moment when a new image downloads, revealing structures never seen before. The realization that a pattern in the data might solve a long-standing puzzle. The satisfaction of understanding something about the universe that nobody knew before. These human elements are integral to science. It's not a cold, impersonal process, but a deeply human endeavour, driven by curiosity, sustained by perseverance, enriched by collaboration, and sometimes tension. The diversity of people working on Webb is also important. Scientists from many countries, from different backgrounds, bringing varied perspectives. Historically, science was dominated by a narrow demographic. But efforts to increase diversity are making the community more inclusive. Different perspectives lead to better science. Someone from a different background might notice a pattern others miss, ask a question others don't think to ask, propose an explanation others don't consider. Diversity is a strength. There are still barriers to overcome. Gender imbalance, racial inequity, accessibility issues for people with disabilities, geographic disparities in resources. Progress is being made, but challenges remain. The scientists working on Webb's data come from this diverse community, each contributing their expertise, their passion, their unique viewpoint. Together, they're unravelling the mysteries of the early universe, building knowledge piece by piece. Appreciating the human side helps us understand that science is a collective human achievement, not the work of isolated geniuses, but of communities of people, each playing a role, supporting and challenging each other, all driven by the desire to understand. When we look at Webb's images, we should remember the thousands of people who made them possible. When we hear about surprising discoveries, we should appreciate the scientists working to understand them. Science is human, beautifully, messily human, and that humanity is what makes it meaningful. We're a species that looks at the stars and wonders. We build telescopes and develop theories. We ask questions and seek answers. Webb is one expression of this very human drive to understand our place in the cosmos. Beyond the science, Webb's discoveries raise deeper questions about knowledge, understanding, and our relationship with the universe. Let's contemplate some of these philosophical dimensions. One fundamental question is about the limits of knowledge. Webb has shown us the universe at times just a few 100 million years after the Big Bang. Could we ever see earlier? Are there fundamental limits to how far back we can look? The cosmic microwave background from 380,000 years after the Big Bang is a kind of horizon. Before that, the universe was opaque to light. We can't see through the CMB to earlier times using electromagnetic radiation. But there are other windows. Neutrinos and gravitational waves could, in principle, carry information from earlier times. Detecting them is extraordinarily difficult but not impossible. Future observatories might extend our view back to the very first moments. Still, there might be ultimate limits. Quantum mechanics suggests that space-time itself becomes ill-defined at the Planck scale, incredibly tiny fractions of a second after the Big Bang. Physics as we understand it might not apply. What happened at the very beginning might be fundamentally unknowable. This raises philosophical questions about the nature of explanation. If we reach limits where physics breaks down, where empirical observation becomes impossible, can we still claim to understand the beginning? Or must we accept mystery? Different philosophical traditions answer differently. Scientific realism holds that we can understand reality as it is, that our theories describe actual features of the universe. Instrumentalism suggests theories are merely tools for prediction, not necessarily describing reality. Webb's discoveries bear on these debates. The fact that we can observe galaxies from 13 billion years ago, essentially watching the universe's childhood, is remarkable. It suggests that empirical science can reach very far indeed. But the surprises, the fact that early galaxies weren't as predicted, remind us that our understanding is always provisional. We might think we know how galaxies form, but the universe can surprise us. Humility is warranted. There's also a question about the uniqueness of our observations. We see the universe from one particular place and time, from Earth in the early 21st century. Observers elsewhere at other times would see different things. If we're seeing surprising early galaxies, it's partly because we're observing at a time when our technology just became capable of detecting them. In another century, with better instruments, we might find even earlier, more surprising objects. This temporal perspective raises questions about progress. Are we approaching a complete understanding of the universe, or will there always be new horizons? New mysteries? History suggests the latter. Every breakthrough reveals new questions. Webb is one expression of this drive. We built a telescope costing billions and taking decades because we wanted to see the early universe. Not for any practical benefit, but because we wanted to know. That's remarkable. It also reflects optimism. Despite challenges on Earth, despite conflicts and problems, we invest in understanding the cosmos. We believe it's worthwhile to explore, to learn, to expand human knowledge. That belief sustains long-term projects like Webb. There's also a perspective shift. Looking at images of galaxies billions of light years away, seeing the universe's vastness and age, can change how we think about ourselves. We're tiny, brief, seemingly insignificant. But we're also the part of the universe that can understand it. We're matter that has become conscious, that can contemplate its origins. In us, the universe knows itself. That's not insignificant, it's profound. This perspective, sometimes called the cosmic perspective, can be both humbling and elevating. Humbling because it shows our smallness, elevating because it shows our connection to something vast and ancient. Webb's images embody this perspective. They show us our cosmic context, our place in space and time. They remind us that we're part of a much larger story, one that began long before us and will continue long after. How we respond to that perspective is up to us. Some might feel overwhelmed or alienated, others might feel wonder and belonging. There's no single right response, each person finds their own meaning. But the opportunity to contemplate these questions, to look at the early universe and wonder about our place in it, is a gift. Webb provides that opportunity, offering images and data that can inspire both scientific inquiry and philosophical reflection. As we explore what Webb has shown us, we're engaging in one of humanity's oldest activities, looking at the sky and wondering. The tools have become more sophisticated, but the fundamental drive is the same. We want to understand the cosmos and our place within it. Let's synthesize what we've learned, building a picture of the universe's first billion years that incorporates both standard models and Webb's surprising discoveries. This is the timeline we're trying to understand. The Big Bang occurs at time zero. The universe is infinitely dense and hot. Within the first tiny fractions of a second, fundamental physics plays out. Particles and forces separate, space inflates rapidly, the basic structure of matter is established. By 1 second after the Big Bang, the universe has cooled enough for protons and neutrons to form. By 3 minutes, nuclear reactions create hydrogen, helium, and traces of lithium. These light elements created in the Big Bang's first minutes persist today, their abundances matching theoretical predictions. For the next 380,000 years, the universe remains opaque, filled with ionized plasma. Photons scatter constantly, unable to travel far. Matter and radiation are tightly coupled, expanding together, cooling together. Then, at 380,000 years, electrons combine with nuclei. Forming neutral atoms, the universe becomes transparent. Light can travel freely for the first time. This is the moment captured in the cosmic microwave background, ancient light now stretched to microwave wavelengths. After this, the universe enters the Dark Ages. It's filled with neutral hydrogen gas. No stars yet, just diffuse matter slowly collapsing under gravity's influence. Dark matter halos form, their gravity attracting ordinary matter into dense clumps. According to standard models, the first stars ignite somewhere between 50 and 200 million years after the Big Bang, when the densest dark matter halos accumulate enough gas for star formation. These are population 3 stars, massive, hot, short-lived. Their ultraviolet radiation begins to ionize surrounding hydrogen, creating bubbles of ionized gas. Their supernova explosions scatter the first heavy elements, enriching the gas. This sets the stage for the next generation of stars and for the first galaxies. The first galaxies, according to models, form between 100 and 400 million years after the Big Bang. Initially small, perhaps containing only millions of stars, they merge and grow, building progressively larger structures. Webb's observations push into this era. Galaxies at redshift z equals 10 are seen as they were about 450 million years after the Big Bang. Galaxies at z equals 15 are from perhaps 250 million years after. We're watching this crucial period directly, and what Webb sees is more activity than predicted. Galaxies appear earlier than expected, more massive than predicted, brighter than anticipated. Star formation seems to have ramped up quickly, more quickly than models suggested. This could mean population 3 star formation occurred earlier and more efficiently. Or it could mean that early star formation in general was more efficient, converting a larger fraction of available gas into stars. Black holes also appear early. growing to millions of solar masses by 400 million years. This suggests either that black hole seeds were larger than expected, or that growth was faster, or both. Reionization, the process of ionizing all the universe's hydrogen, proceeds during this time. Starting as small bubbles around the first stars and galaxies, the ionized regions merge, eventually pervading all of space. Observations suggest reionization was largely complete by about 1 billion years after the Big Bang. Webb is observing galaxies during and after reionization, seeing both the sources driving it and the effects of the ionized environment on galaxy formation. The interplay between stars, ionization and galaxy assembly is complex. By 500 million years after the Big Bang, according to Webb's observations, the universe contained numerous galaxies, some quite massive. Star formation was vigorous. Black holes had grown substantially. Structure was well established. By 1 billion years, large galaxies existed, perhaps not as large as today's giants, but substantial nonetheless. The hierarchical assembly of structure was well underway. The universe was no longer in its infancy, but entering its youth. The first billion years were crucial. This is when the universe transitioned from a dark, homogeneous gas to a structured cosmos filled with galaxies and stars. Understanding this transition is key to understanding everything that followed. Webb has given us unprecedented access to this era. We're watching the transition happen, seeing galaxies assemble, witnessing the birth of structure. The view is clearer than ever before, even as it raises new questions. The puzzles Webb has revealed, the massive early galaxies, the early black holes, the high star formation rates. These aren't contradictions, but challenges. They're telling us we don't have all the details right yet. Our models need refinement. But the basic story holds. The universe expanded from a hot, dense beginning. Structure formed through gravitational collapse. Stars ignited, galaxies assembled. The cosmos evolved from simplicity to complexity. This narrative is secure. Webb is helping us fill in the timeline with greater accuracy, adding detail, correcting errors, revealing subtleties we missed. The first billion years are coming into focus, showing us the universe's childhood in unprecedented clarity. As observations continue and models improve, the picture will sharpen further. We'll understand better when and how each stage occurred, what drove the processes, how everything connected. The story will become richer and more accurate, and that story is our story too. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were created in stars that formed during this early era and later ones. We're made of material forged in the cosmic crucible. Understanding the universe's first billion years is understanding our own origins, tracing the chain of events that led from the Big Bang to us. Webb is helping us read that history, revealing our cosmic heritage. To fully appreciate Webb's achievements, it helps to compare it with its predecessor, the Hubble Space Telescope. Understanding the differences shows why Webb can see things Hubble couldn't, and why its discoveries are so significant. Hubble launched in 1990, revolutionizing astronomy. For over 3 decades, it has provided stunning images and groundbreaking science. Hubble's sharp vision, free from atmospheric distortion, revealed galaxies, nebulae, and distant objects with unprecedented clarity. But Hubble observes primarily invisible and ultraviolet light, wavelengths our eyes can see. It has some infrared capability, but limited. This is fine for nearby objects, but limits how far back in time Hubble can see. Webb can achieve similar depth in much less time, because its larger mirror collects more light, and it sees different objects. Heavily dust-obscured galaxies invisible to Hubble, extremely distant galaxies whose light has shifted beyond Hubble's range, cool objects like brown dwarfs and distant planets. Both telescopes are in space to avoid atmospheric interference, but in different locations. Hubble orbits Earth at about 550 kilometers altitude. Astronauts have visited it 5 times to repair and upgrade instruments, extending its life. Webb, at L2 a million miles from Earth, is beyond reach of any current spacecraft. It had to work perfectly from the start, which it has. But it can't be serviced. When it runs out of fuel for maintaining its orbit, or when instruments degrade, its mission will end. Hubble has studied many topics beyond cosmology: stars, planets, nebulae, nearby galaxies. Its versatility made it invaluable across astronomy. Webb is also versatile, studying exoplanet atmospheres, star formation and more, but it's particularly optimized for observing the distant universe. The two telescopes complement each other. Hubble sees shorter wavelengths, Webb longer. Combining observations from both provides a more complete picture than either alone. Some objects have been observed by both, allowing comparison across a wide range of wavelengths. For early galaxy studies specifically, Webb has advantages that make it superior. It sees galaxies Hubble couldn't detect, resolves structures Hubble could barely glimpse, measures properties through spectroscopy that was impossible for Hubble. This is why Webb's observations are revealing surprises. We're not just seeing the same galaxies more clearly, we're seeing a different population, one that was mostly invisible to Hubble. This new view naturally reveals phenomena we didn't know about. Hubble's legacy is secure. It transformed our understanding of the universe and continues producing excellent science. When it finally ceases operation, it will be remembered as one of the most successful scientific instruments ever built. Webb is building on that legacy. It's the next step, extending our view farther, seeing deeper, revealing more. Together, Hubble and Webb span wavelengths from ultraviolet through infrared, giving us a comprehensive view of the cosmos. There's also the Spitzer Space Telescope, which operated in infrared before being retired in 2020. Spitzer provided valuable infrared observations for years, but its mirror was much smaller, just 85 centimeters, limiting how faint it could detect. Webb is essentially Spitzer's successor, with a far larger mirror and more advanced instruments. The improvement from Spitzer to Webb is as significant as from Hubble to Webb in their respective wavelength ranges. Future telescopes will someday surpass Webb, seeing even farther, detecting even fainter objects. That's the nature of technological progress. Each generation builds on the previous one, pushing capabilities further. But for now, Webb represents the cutting edge. It's the most powerful telescope we have for observing the early universe. The discoveries it's making will shape astronomy for decades, even as future telescopes eventually exceed its capabilities. The comparison with Hubble reminds us how far we've come. Hubble opened our eyes to the deep universe. Webb is opening them further, showing us cosmic epochs Hubble could barely reach. The view keeps getting better, and our understanding keeps growing. While Webb's observations of early galaxies have grabbed headlines, the telescope is making important discoveries across astronomy. Let's briefly explore some other areas where Webb is advancing knowledge, showing the breadth of its capabilities. Exoplanet atmospheres are one major research area. Webb can analyze starlight passing through a planet's atmosphere as the planet transits in front of its star. By examining which wavelengths are absorbed, astronomers can identify molecules in the atmosphere: water, carbon dioxide, methane, and others. This provides unprecedented detail about exoplanet compositions. For the first time, we're characterizing the atmospheres of planets orbiting other stars, learning what they're made of, whether they might be habitable. Webb has detected carbon dioxide in a gas giant's atmosphere, found water vapor in several planets, and even detected hints of more complex molecules. Each detection adds to our understanding of planetary diversity and the conditions that might support life. Star formation is another focus. Webb observes the dusty clouds where stars are born, seeing through the dust to watch the process unfold. It can see protostars, newly forming stars still gathering mass, and protoplanetary disks. The swirling disks of gas and dust around young stars where planets form. It also observes the centres of nearby galaxies, studying supermassive black holes and their effects on surroundings. The interplay between black holes and galaxy evolution is a major research area, and Webb provides crucial data. Gravitational lensing is used not just for studying distant galaxies, but also for mapping dark matter. By examining how light from background galaxies is distorted by foreground galaxy clusters, astronomers can map the clusters' mass distributions, revealing where dark matter is concentrated. Supernovae and other transient events are observed when possible. Webb isn't designed for surveying large areas of sky rapidly, so it doesn't discover transients itself, but when notified of interesting events by other telescopes, it can follow up, providing detailed spectra. There are also serendipitous discoveries, finding unexpected objects in images taken for other purposes. With every deep image, Webb sees thousands of galaxies, any of which might be interesting. Sorting through this wealth of data reveals surprises. For example, gravitationally lensed background galaxies appear distorted into arcs or multiple images. These aren't the main targets, but provide bonus science, sometimes revealing very distant galaxies that were magnified by the foreground lens. Webb is also detecting brown dwarfs, objects between planets and stars in mass, too small to sustain hydrogen fusion but larger than giant planets. Their cool temperatures make them bright in infrared, and Webb's sensitivity finds them at distances where previous telescopes couldn't. All these discoveries demonstrate Webb's versatility. It's not a one-trick telescope. Its infrared sensitivity, large mirror and suite of instruments make it valuable across astronomy. But for the public, and even for many scientists, the early universe observations are the most exciting. They address fundamental questions. How did the first galaxies form? When did the first stars ignite? How did structure emerge from the Big Bang's uniformity? These questions have captivated humans for millennia. Different cultures created myths about cosmic origins. Now we're answering those questions scientifically, using tools like Webb to observe the actual early universe. The discoveries are ongoing. Webb's mission is expected to last at least 10 years, possibly longer if fuel reserves hold out. Each year will bring new observations, new data, new insights. Some of the most important discoveries might not even be anticipated. History shows that when we build new instruments with capabilities beyond previous ones, we find things we didn't expect. Webb will likely continue surprising us. The breadth of Webb's science also justifies the investment. It's not just answering one question, but many, advancing multiple fields simultaneously. The tens of billions spent over decades are yielding dividends across astronomy. And the images themselves have value beyond science. They're beautiful, inspiring awe and wonder. They connect people to the cosmos, providing a sense of our place in the universe. That intangible benefit, harder to quantify than scientific papers, is also real and important. Webb is humanity's eye on the cosmos, revealing the universe in infrared light, showing us things we've never seen before. From exoplanet atmospheres to the earliest galaxies, from nearby planets to the most distant reaches of space, it's expanding our view and our understanding. Webb's cost, over $10 billion, raises questions about funding priorities and the value of space science. These are important questions worth contemplating honestly and openly. $10 billion is a lot of money. It could fund many other things: schools, hospitals, infrastructure, poverty relief. Why spend it on a telescope? This question deserves a serious answer. First, perspective on the amount. Spread over the 25 years of development, Webb cost about $400 million per year. The US federal budget in recent years has been around $4 to $5 trillion. Webb represents less than 0.1% of annual federal spending, a tiny fraction. Still, $400 million per year could do a lot elsewhere. The justification comes from what we gain. Scientific knowledge has value in itself, expanding human understanding. Space exploration inspires people, educates students, advances technology. Webb has already driven numerous technological innovations. The mirror deployment mechanism, the sun shield, the cryogenic instruments all require developing new technologies. these often find applications elsewhere, in medical devices, communications, materials science. Moreover, the money wasn't poured into space and lost. It employed thousands of people, engineers, scientists, technicians in the US and partner countries. Those people spent their salaries supporting families and communities. The economic impact extended beyond the direct spending. Space science also inspires young people to pursue STEM careers. Images from Webb spark interest in astronomy, physics, engineering. Some students seeing these images will become the scientists and engineers of tomorrow, contributing to technological progress. There's also international collaboration. Webb is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. Cooperation on such projects builds relationships, demonstrates that nations can work together on peaceful endeavours. In troubled times when international tensions run high, projects like Webb show what's possible when countries collaborate towards shared goals. The symbolic value of cooperation shouldn't be underestimated. But these justifications might not satisfy everyone. Some argue that space science is a luxury, that we should fix problems on Earth before exploring space. This perspective is understandable, especially for those struggling with poverty, inequality, or other challenges. The counter-argument is that it's not an either-or choice. We can do both. Address Earth's problems and explore space. The amount spent on Webb is small compared to other expenditures. If Webb had been cancelled, the money wouldn't necessarily have gone to solving poverty or climate change. It might have gone elsewhere or not been spent at all. Future projects will face similar scrutiny. Trust in science is earned, not automatic. Scientists must demonstrate that investments yield worthwhile returns, whether in knowledge, technology, inspiration, or practical benefits. There's also the question of priorities within science. Should we spend $10 billion on one telescope or spread it across many smaller projects? Again, there's no simple answer. Large flagship projects like Webb do things smaller projects can't, but many small projects together can also be powerful. A balanced portfolio is probably best. Some large projects, some medium, many small. Diversity of approaches, scales, and goals strengthen science overall. Webb was prioritised because it promised transformative science. It would see things no other telescope could see, answering questions no other mission could address. That promise has been fulfilled. The discoveries justify the investment. But we should also be honest about uncertainties. Not every major project succeeds. Some fail technically or scientifically. Risk is inherent. We can't know in advance which projects will yield breakthroughs. This is why careful planning, peer review, and oversight matter. Webb underwent extensive reviews, each checking technical feasibility, scientific value, and cost-effectiveness. These processes aren't perfect, but they reduce risk. Looking forward, future projects will cost billions too. The next generation of space telescopes, missions to other planets, searches for life beyond Earth, all require substantial investment. How we prioritise these will shape future discoveries. Public engagement helps. When people understand and value space science, they support it. When they don't, funding becomes vulnerable. Scientists have a responsibility to communicate why their work matters. Webb's beautiful images and exciting discoveries help this communication. They show concretely what space science produces, making the value tangible. Not everyone cares about redshift z equals 13 galaxies, but many appreciate stunning images of the cosmos. In the end, the question of whether Webb was worth the cost is partly subjective, depending on what we value. But objectively, it's producing world-class science, advancing human knowledge, inspiring wonder, and demonstrating technological prowess. By those measures, it's succeeding admirably. Science never provides absolute certainty. Every measurement has uncertainties, every model has assumptions, every conclusion is provisional. Webb's discoveries remind us to be comfortable with this uncertainty, to appreciate what we know while acknowledging what we don't. When scientists say they're puzzled by Webb's early galaxies, they're not admitting failure. They're being honest about the limits of current understanding. This honesty is a strength, not a weakness. Accepting uncertainty doesn't mean accepting ignorance. We know a tremendous amount. The Big Bang, cosmic expansion, galaxy formation, these are well established. The uncertainties are in the details, not the broad framework. It's like knowing Earth orbits the Sun, certain, while debating whether a particular asteroid might impact us next century, uncertain. Both statements coexist: secure knowledge and open questions. Webb's early galaxy discoveries fall into this category. We know these galaxies exist and are very distant, certain, confirmed by multiple observations. We don't fully understand how they formed so early, uncertain, subject to ongoing research. Living with this mix of knowledge and ignorance is the human condition. We've learned much, but not everything. We understand much, but not all. Each answer raises new questions. The process never ends. There's wisdom in accepting this. It prevents arrogance, the belief that we've figured everything out. History is littered with examples of people who thought they knew all answers, only to be proven wrong. Humility in the face of the universe's complexity is appropriate. It also keeps science dynamic. If we thought we knew everything, research would stop. But recognizing what we don't know drives investigation. The mysteries are what make science exciting. For individuals, comfort with uncertainty extends beyond science. Life is full of unknowns. We don't know the future, can't predict every outcome, face ambiguous choices. Learning to be okay with not knowing, to make decisions despite uncertainty, is valuable. Science models this. Scientists make progress despite incomplete knowledge. They act on best current understanding while remaining open to revision. This adaptive approach is worth emulating in other domains. Webb's discoveries will eventually be understood. Astronomers will figure out why early galaxies are more massive than predicted. Models will be refined. The mystery will be solved, but new mysteries will replace it. That's the beauty of science. It's an endless frontier. Each discovery opens new questions. We'll never run out of things to learn, never reach a point where everything is known. The universe is too vast, too complex, too surprising. Embracing this endless inquiry is liberating. We don't need to have all answers to appreciate what we know. We don't need certainty to make progress. We can be comfortable saying quote 7 while working toward understanding. Webb is teaching us about the early universe, but it's also teaching us humility. The universe is more complex than our models captured. That's okay. We adjust, we learn, we improve. That's the process. As you drift towards sleep, you can rest in this uncertainty. The universe doesn't require you to understand it completely. Your questions don't need immediate answers. Mystery is not a problem to solve, but a condition to accept, even embrace. Beyond all the science, beyond the theories and measurements, there's something profound about the simple act of looking deeper into space than we've ever looked before and seeing what's there. Let's contemplate the beauty of discovery itself. Webb's images are stunning. Even without understanding the science, anyone can appreciate their aesthetic power. Galaxies scattered across darkness, glowing in oranges and blues and reds, each one an island of billions of stars, each with its own shape and character. There's beauty in the patterns, spiral galaxies with elegant arms winding outward, elliptical galaxies glowing smoothly, irregular galaxies showing chaotic structure. The diversity is remarkable, each galaxy unique yet following physical laws. The colours in Webb's images are meaningful. They're not arbitrary artistic choices, but represent real information. Different wavelengths are mapped to visible colours, allowing our eyes to see infrared light. Red regions might be dust, blue regions young stars, the palette conveying physics. But the beauty transcends the physics. There's something moving about seeing objects billions of light years away, knowing that the light reaching Webb's mirror left those galaxies when the universe was young, travelling across expanding space for billions of years to reach us. Each photon captured by Webb is a messenger from the ancient universe. It originated in a star that lived and died billions of years ago, travelled unimaginable distances, navigated through expanding space, and finally arrived at our telescope. We're reading messages from deep time. This connects us to the cosmos in a visceral way. We're not separate observers but participants. The atoms in our bodies were forged in stars, possibly in galaxies not unlike those Webb observes. We're made of star stuff, as Carl Sagan famously said, literally connected to the cosmic story. There's also beauty in human achievement. Webb exists because thousands of people dedicated years of their lives to building it. Their creativity, persistence, and skill made these observations possible. The images represent human capability at its finest. The collaboration across nations is beautiful too. Americans, Europeans, Canadians, working together towards shared goals. In a world often divided, space exploration demonstrates what cooperation can achieve. Webb is a monument to international partnership. And there's beauty in curiosity itself, the impulse to look and wonder. Humans have gazed at stars for millennia, telling stories, asking questions, seeking understanding. Webb is our species' latest expression of that ancient impulse, using modern technology but driven by timeless curiosity. The surprise of discovery adds another layer. Webb finding unexpected galaxies reminds us that nature is creative beyond our imagination. We can theorize and model, but reality often exceeds our predictions. The universe is richer than our minds can fully capture. This should inspire humility and wonder together. Humility because our theories proved incomplete, wonder because the universe revealed something new. Both are appropriate responses to the mystery and magnificence of existence. There's beauty in questions too, not just answers. The puzzles Webb has revealed are invitations to think deeply, to question assumptions, to explore possibilities. Questions drive discovery, opening paths to new knowledge. A question like Quote 8 might seem technical, but it touches on fundamental issues. How does structure emerge from simplicity? How does complexity arise? These are questions that extend beyond astronomy to philosophy, to our understanding of existence itself. Art and science aren't as separate as sometimes supposed. Both seek to understand and express truth about reality. Artists do it through emotion and aesthetics, scientists through logic and measurement. But the impulse is similar, and the results can be equally moving. Webb's images blur this boundary. They're scientific data, yes, but they're also works of art, compositions of colour and form that evoke emotional responses. The beauty serves the science by capturing attention, but it's real beauty, not just decoration. Children seeing Webb's images might be inspired to become scientists, or artists, or philosophers. The inspiration doesn't need a specific channel. What matters is that wonder is kindled, that sense that the universe is vast and strange and worth exploring. That sense of wonder is precious. Daily life can dull it, routine and distraction pulling our attention to the immediate. But images of distant galaxies can break through, reminding us of the larger context, the cosmic perspective. Looking at Webb's deep fields, seeing thousands of galaxies each containing billions of stars, it's hard not to feel something, awe at the scale. Curiosity about those distant worlds, perhaps a little vertigo realizing how small we are, but also connection. Those galaxies are made of the same elements as us. They follow the same physical laws. In a sense, they're family, distant cousins in the cosmic tree of structure. We're all part of the same universe, all consequences of the Big Bang. This connection extends through time too. The galaxies Webb observes existed billions of years ago. We're seeing them in their youth. They've evolved since, changed in ways we can't yet see because the light showing those changes hasn't reached us yet. But we can imagine their futures. Some have probably merged with other galaxies by now. Some have formed trillions of stars. Perhaps some contain civilizations. beings looking out at their universe just as we look at ours. This speculation is grounded in real observations. The galaxies are real. Their stars are real. If physics allows life here, it probably allows it there. We might not be alone in contemplating the cosmos. That possibility adds another dimension of wonder. Somewhere among those distant galaxies, other eyes might be looking back, asking similar questions, building similar telescopes, seeking to understand their cosmic origins just as we seek to understand ours. We'll probably never know. The distances are too vast for communication or travel with any foreseeable technology, but the possibility itself is profound. We might be one conscious species among many, all seeking understanding, all part of the universe knowing itself. Webb's discoveries are beautiful because they expand our knowledge, challenge our understanding, reveal unexpected complexity, and connect us to the cosmos. They remind us that we're part of something vast and ancient and ongoing. As we move toward the end of our journey together tonight, we can hold this beauty in mind. The images, the science, the questions, the sense of wonder. These are gifts, opportunities to contemplate our place and our connection to everything. In these final chapters, let's slow down even more, moving into contemplation and rest. Let's think about how fortunate we are to live in a time when we can observe the early universe, when telescopes like Webb exist. For most of human history, the night sky was a mystery. People saw stars and planets, the moon and occasional comets, but had no way to know what they were looking at. The stars might be holes in a celestial sphere, fires on a distant dome. Anything the imagination could conjure. This is extraordinary. We're among the first generations of humans who can observe the universe's childhood. Our ancestors couldn't. Our distant descendants will, but they'll have different technologies, different capabilities. We're living in this particular moment of discovery. There's privilege in this. We happen to be alive during the age of space telescopes, during the early 21st century when capabilities finally match ambitions. A generation earlier, and Webb wouldn't have existed. We might have had to wait our whole lives for these discoveries. But we don't have to wait. The images are here, available to anyone with an internet connection. Webb's data is public, shared freely. Anyone can see what Webb sees, can contemplate the same ancient galaxies the professional astronomers study. This democratization of access is new. Previous generations, even with telescopes, could only observe if they had access to major observatories. Now, the deepest views of the cosmos are available to everyone, anywhere. Of course, understanding the images requires education, context. Not everyone has the background to interpret spectra or calculate redshifts. But the basic experience, seeing distant galaxies, appreciating their beauty and significance, that's accessible to all. There's also privilege in being human at all, conscious beings capable of contemplating the cosmos. The universe is mostly unconscious, atoms and energy following physical laws without awareness. We're the exception, matter that can think about itself. This consciousness allows us to appreciate the universe in ways it can't appreciate itself. A galaxy doesn't know it's beautiful. A star doesn't wonder about its origins, but we do. We can look at Webb's images and feel wonder, ask questions, seek understanding. Some might find this perspective humbling to the point of insignificance. We're tiny, brief, irrelevant in the cosmic scale. One planet among billions, one species among countless possibilities, here for a moment in cosmic time. But another perspective is that our consciousness gives us unique value. We're the universe's way of knowing itself, experiencing beauty, creating meaning. Without consciousness, all the galaxies and stars would exist but never be appreciated, never be understood. From this view, being human, being alive now, having access to Webb's observations, these are gifts. We didn't earn them through any merit of our own. We're fortunate to exist at this time and place with these capabilities. What do we do with this privilege? We can choose to pay attention, to learn, to appreciate. We can choose wonder over indifference, curiosity over apathy, gratitude over entitlement. We can share what we learn, teaching others, inspiring curiosity in the next generation. We can support science, recognizing its value for expanding knowledge and enriching human experience. We can also simply be present with the experience. Looking at an image of galaxies from the early universe, we can pause, breathe, feel whatever arises, or perhaps curiosity, a sense of connection or of perspective. These moments of contemplation are valuable in themselves. They pull us out of daily concerns, expand our awareness beyond the immediate, remind us of the larger context we exist within. In a busy world full of demands and distractions, taking time to contemplate the cosmos might seem like a luxury. But it's a human need, this connection to something larger than ourselves, this sense of wonder and meaning. Webb provides an opportunity for this connection. Its images are windows into deep space and time, invitations to contemplate cosmic origins and our place within them. Whether we accept that invitation is up to us. As you rest here tonight, you're accepting it. You've spent time learning about Webb's discoveries, thinking about early galaxies, contemplating the universe's history. That's a gift you've given yourself, time for wonder and learning, and it's a gift to yourself too. Not everyone takes this time. Many people go through life without ever pausing to contemplate the cosmos. You're choosing differently, valuing understanding and wonder. That choice connects you to a long tradition. Humans have always looked at the stars and wondered. You're continuing that tradition, using modern tools but driven by ancient impulses. You're part of the story of human curiosity and discovery. Rest in that connection. You're privileged to live in this time, to see what Webb has revealed, to participate in humanity's ongoing quest to understand the universe. That privilege comes with no obligation except, perhaps, to appreciate it. As we move deeper into rest, let's embrace the questions that remain unanswered, the mysteries that persist even after all we've learned. Not every question needs an answer. At least not right now. Why does the universe exist at all? Why something rather than nothing? This is perhaps the deepest question, and science can't fully answer it. We can trace the universe back to the Big Bang, but we can't explain why there was a Big Bang, why physical laws exist, why existence itself is. What happened before the Big Bang? Did time itself begin with the Big Bang, making, quote, 9 meaningless? Or did something exist earlier, some previous state or cycle? Various theories propose different answers, but we have no observations to test them. Will the universe end? Current evidence suggests it will expand forever, gradually cooling and dimming as stars burn out and black holes evaporate. But this is based on assumptions about dark energy that might be wrong. The ultimate fate remains uncertain. These are big questions, perhaps unanswerable with current knowledge. But there are also smaller mysteries in what Webb has shown us. How exactly did those early massive galaxies form? What process accelerated their growth? We'll probably answer these eventually, but not yet. Why do we find mystery uncomfortable? Perhaps because it feels like incomplete knowledge, something we should fix. But mystery can also be beautiful, an invitation to wonder rather than a problem to solve. Many cultures and traditions embrace mystery, finding value in the unknown. The mystical branches of various religions speak of ineffable truths beyond words or concepts. Poetry often works by suggestion rather than explanation, pointing toward meanings that can't be stated directly. Science, in contrast, seeks to reduce mystery, to explain the unknown. This is valuable and has expanded human knowledge immensely. But even science encounters limits, questions that may be permanently unanswerable or temporarily beyond reach. Living with these questions, accepting them without anxiety, is a kind of wisdom. We don't need to know everything to appreciate what we do know. We can be comfortable with partial understanding. Webb's discoveries are partial understanding. We see early galaxies but don't fully understand them yet. That's okay. The observations are real. The images beautiful. The question's interesting. The incomplete understanding doesn't diminish the value. As you drift towards sleep, you can let these questions float through your mind without grasping for answers. Why does the universe exist? We don't know. How did consciousness arise? We don't know. Are we alone? We don't know. And that's okay. The questions themselves are meaningful even without answers. They remind us that reality is deeper than our current comprehension, that there's always more to discover, to wonder about, to contemplate. Some questions you might never see answered in your lifetime. The universe is vast and human lives are short. We're each given a brief window to observe and understand. What we learn in that window is what we get. But that window is extraordinary. You live in an age when we can observe galaxies from the early universe. That's a gift previous generations didn't have. Future generations will know more, but they won't have the experience of living through these particular discoveries. Rest in the questions. Let them be present without demanding answers. Mystery is not a burden, but a companion, a reminder that the universe is larger than our understanding, more complex than our models, more wonderful than we can fully grasp. Sleep can come easier when we release the need to know everything, when we accept that some things remain mysterious, when we're comfortable with partial understanding. The universe will continue whether we understand it or not. Our task is simply to appreciate it while we can. There's something deeply comforting about cosmic perspective, about remembering our place in the vastness of space and time. Let's rest in that perspective, finding peace in the scale that surrounds us. Your worries, whatever they are real and valid. Personal concerns matter. The challenges you face are genuine. But they're also temporary, local, small in cosmic scale. This isn't to diminish them, but to contextualize them. 100 years from now, your specific concerns will be resolved one way or another, simply by the passage of time. 1,000 years from now, your entire civilization's current concerns will be historical footnotes. 1,000,000 years from now, our species might not exist in recognizable form, but the universe will continue. Galaxies will orbit, stars will shine, planets will circle their suns. The physical processes playing out across cosmic scales are indifferent to human concerns. They proceed according to natural law, unconcerned with our anxieties. This indifference can feel cold, but it can also be freeing. You don't bear responsibility for the cosmos. It doesn't require your worry or your management. It simply is, vast and ancient and ongoing. The early galaxies Webb observes existed billions of years before humans evolved. They'll continue existing billions of years after we're gone. Our presence or absence makes no difference to them. We're observers, not participants in their story. This perspective can reduce anxiety. Whatever you're worried about, cosmic history continues regardless. The sun will rise tomorrow. The Earth will orbit. The galaxy will rotate. These certainties persist despite human concerns. There's also comfort in continuity. We're part of an unbroken chain extending back to the Big Bang. The atoms in your body were forged in stars, perhaps in galaxies, Webb observes. You're made of ancient cosmic material, connected to the deepest history. This connection means you're not separate from the universe, but part of it. You're not facing it from outside, but experiencing it from within. Your consciousness is the universe becoming aware of itself, thinking about its own history and nature. From this perspective, there's no separation between you and the cosmos. The same physics that governs galaxies governs your body. The same elements that make stars make you. You're a local concentration of cosmic matter and energy, temporarily organized, briefly conscious. This might sound impersonal, but it can be deeply comforting. You belong here. You're not an alien in the universe, but native to it, as much a part of reality as any star or galaxy. Your existence is natural, arising from the same processes that created everything else. And your consciousness, your ability to think and feel and wonder, is part of the universe too. When you contemplate the cosmos, the universe is contemplating itself through you. Your thoughts about distant galaxies are cosmic self-reflection. The cosmic perspective also reveals that change is constant. Galaxies merge, stars die, new stars form. Nothing remains static. The universe is dynamic, always evolving, never fixed. Your life is part of this change. You grow, learn, age, transform. The person you were 10 years ago is different from who you are now. The person you'll be 10 years hence will differ from your current self. This is natural, part of the cosmic pattern of change. Accepting this impermanence can reduce suffering. If nothing is permanent, then current difficulties will pass. Pain is temporary, challenges are temporary. Everything changes, including circumstances that currently seem unchangeable. Recognizing this can create presence. Since each moment is unique and temporary, it's worth experiencing fully. Not rushing to the next thing, but being here, now, in this specific moment of existence. The cosmic perspective doesn't make personal concerns irrelevant. You still need to live your life, address your challenges, care for yourself and others. But the perspective can provide context, reducing the intensity of worry, creating space for peace. When you feel overwhelmed, remember the galaxies. Billions of them, each containing billions of stars all existing in vast space, following natural laws, indifferent to your specific situation. This vastness is not threatening, but liberating. You're part of it, held by it, connected to it. Your consciousness arose from cosmic processes. Your body is made of star stuff. Your brief life is one moment in the universe's long story. You're both infinitesimally small and infinitely valuable, both temporary and part of something eternal. Rest in this paradox. Let the cosmic scale wash over you, not drowning you but floating you, supporting you with its vastness. Your home in the universe. Always have been, always will be as long as you exist. And when you cease to exist, as eventually everyone does, your atoms will return to the cycle. They'll become part of something else, continuing the pattern. Nothing is truly lost, only transformed. You're part of the eternal flow of matter and energy through space and time. This isn't morbid, but peaceful. You're connected to everything, part of the cosmic whole. Rest in that connection, that belonging, that vast perspective that holds your small life within infinite space. As we approach the end of our journey, let's think about light itself, the photons that travelled billions of years to reach Webb's mirror, the light that makes all astronomy possible. There's something to be grateful for in light. Light is extraordinary. It's both wave and particle, moving at the universe's speed limit, carrying information across cosmic distances. Without light, the universe would be dark and unknowable. We'd be trapped on our planet with no way to learn about anything beyond. But light exists, and it travels. Photons from distant galaxies journey across space, maintaining their information, arriving at our telescopes with stories to tell about where they came from, when they left, what they encountered along the way. This single photon, among billions Webb collects, contributes to an image. Combined with countless others, it helps form the pictures we see, the spectra we analyse, the science we do. There's something profound in this journey. The photon's voyage spans most of cosmic history. It's a messenger from the ancient universe, carrying news of conditions billions of years ago. And light is democratic. It doesn't matter who you are, where you're from, what your background is. If you build a telescope and point it at the sky, light will reach you just as it reaches professional astronomers. The photons don't discriminate. This is why astronomy is possible. Light reveals the universe to anyone who looks. Different wavelengths require different detectors, but the principle is universal. Observe light. Learn about its source. This simple fact underpins all astronomy. We should be grateful that the universe is transparent to light. If space were opaque, filled with obscuring material, we couldn't see distant objects. We'd be blind beyond our local region. But space is mostly empty. and light passes through freely. We should be grateful that light speed is finite but fast. If light travelled infinitely fast, we couldn't look back in time. We'd always see everything as it is now. If it travelled much slower, the observable universe would be tiny. The actual speed of light is perfect for allowing cosmic observation. We should be grateful for the electromagnetic spectrum's range. Different wavelengths reveal different phenomena. Radio shows cold gas, infrared shows dust and distant galaxies, visible shows stars, ultraviolet shows hot objects, X-rays and gamma rays show energetic processes. Together, these wavelengths give us a complete picture. We should be grateful for the sun, our local star, whose light makes life possible on Earth. Every photon of sunlight carries energy from nuclear fusion in the sun's core, energy that drives photosynthesis, weather, climate, ultimately supporting all life. We should be grateful for our eyes, evolved to detect visible light, giving us direct perception of our surroundings, and for our minds capable of interpreting that light, creating mental models of the world based on the photons entering our eyes. We should be grateful for the technologies we've developed to extend our vision. Telescopes, cameras, spectrographs, all tools for capturing and analysing light. Webb is the culmination of centuries of optical development, a triumph of human ingenuity. Light connects us to everything we observe. When you look at a star, photons that left that star minutes, years, or centuries ago are entering your eye. You're seeing across time, directly perceiving the past. When you look at Webb's images, you're seeing light that travelled billions of years. Your eyes or screen are displaying information carried by ancient photons. You're connected across cosmic distances and times through light. This connection is tangible, not metaphorical. The photons are real, their journey is real, the information they carry is real. You're genuinely observing the ancient universe, witnessing its history. There's gratitude in this realization. The universe could have been opaque, but it's transparent. It could have been dark, but it's filled with light from billions of galaxies. It could have been incomprehensible, but light carries information we can decode. As you rest, you can appreciate light, the gentle glow from whatever device you're using, the ambient light in your room, if any. The photons continually washing over you, reflected from surfaces, emanating from sources, connecting you to your immediate environment. And you can think about the deeper light, the cosmic background of photons from the Big Bang, the starlight from our galaxy, the light from distant galaxies that Webb has captured. All of it is part of the same phenomenon, electromagnetic radiation in various forms. Light makes the universe knowable. It makes Webb's discoveries possible. It makes vision possible. It makes life possible through sunlight driving photosynthesis. We should be grateful for this fundamental aspect of reality. Rest in the light. Let it be a comfort, a connection, a gift. Light has travelled billions of years to show you the early universe. Light surrounds you always, carrying information, making observation possible. Light is the messenger, the revealer, the connector. Sleep can come gently, peacefully. With gratitude for light and all it reveals, all it makes possible, all it connects. The universe is luminous, filled with photons travelling everywhere, carrying stories, waiting to be observed by eyes and instruments. You're part of this luminous universe, both receiving light and emitting it as thermal infrared. You're woven into the pattern of light and matter, temporary but real, small but connected, brief but part of something eternal. In these final quiet moments, let's simply rest in wonder, without analysis or explanation, just the pure experience of contemplating what Webb has shown us. Billions of galaxies scattered across space and time, each one a vast collection of stars, each star potentially with planets, each planet a world of its own. The scale is incomprehensible, yet it's real. The early universe seen directly through Webb's eyes, galaxies forming just hundreds of millions of years after the Big Bang. light from that distant time reaching us now, ancient photons carrying ancient information. The surprise of discovery, scientists expecting one thing, finding another, models proven incomplete, understanding refined. This is how knowledge grows, through observation and revision. The human achievement. Thousands of people over decades building a telescope that works perfectly, 1,000,000 miles from Earth. The collaboration, the dedication, the skill required. This is humanity at its best, the mystery that remains. We don't fully understand the early massive galaxies. We don't know everything about cosmic dawn. Questions persist, inviting further research, further wonder. The beauty of the images themselves, colours and shapes, light and shadow, galaxies glowing against darkness. Each image a work of art created by nature and revealed by technology. The connection across time. Those galaxies existed billions of years ago. We see them now. Our observations link past and present, bridging cosmic time through light, the privilege of knowing. We live in an age when such observations are possible. Our ancestors couldn't see these things. We can. This is a gift of the present moment. The vastness of space. Billions of light years in every direction. More galaxies than we can count. More stars than grains of sand on all Earth's beaches. The universe is unimaginably large. The depth of time. 13.8 billion years since the Big Bang. Billions of years of cosmic evolution. Generations of stars living and dying. The slow assembly of structure from simplicity. The perseverance of curiosity. Humans have always looked at the sky and wondered. We still do. We build bigger telescopes, develop better theories, ask deeper questions. This drive continues. The comfort of perspective. Our concerns are real but temporary. The universe continues regardless. This vastness can be overwhelming or liberating depending on how we approach it. The peace in acceptance. We don't need to understand everything. We can be comfortable with mystery. We can appreciate what we know while accepting what we don't. The wonder of consciousness. We're matter that can think about matter. Consciousness contemplating the universe. This is extraordinary, perhaps rare, certainly valuable. The gratitude for existence. We exist at all. We're conscious. We can observe and wonder. These are gifts not earned, simply given by the fact of being alive now. Rest in all of this. Let the wonder wash over you without needing to grasp it, understand it, or even fully appreciate it. Just let it be present, part of your awareness as you drift towards sleep. The galaxies are out there, continuing their existence whether we observe them or not. The universe expands, evolves, continues its ancient dance, and you're part of it, briefly conscious, temporarily aware, connected to it all. There's nothing you need to do, no problem to solve, no answer to find. Just rest, breathe, be present with the wonder. The universe is vast and old and mysterious and beautiful. You're a small part of it, but you're part of it nonetheless. Sleep can come now, gently, peacefully. Let your body relax completely. Let your thoughts drift like stars in cosmic currents. Let the wonder remain, quiet and present as you transition into rest. The universe will be here tomorrow, still vast, still mysterious, still wonderful. Webb will continue observing, collecting ancient light, revealing cosmic secrets. The quest for understanding will continue, but for now, just rest. Rest in the wonder, in the vastness, in the mystery and beauty of existence. Rest knowing that you're part of something larger, connected to cosmic history, brief but real, small but meaningful. Let the images of distant galaxies fill your mind as you drift. See them glowing in the darkness, beautiful and serene. Feel your connection to them, through the atoms in your body, through the light reaching your eyes, through the shared fabric of space and time. Rest, peaceful and content, held by the universe. part of the cosmic whole. Wonder and sleep, complementary states. Both valuable, both gifts. Let wonder carry you into sleep, gentle and natural, like starlight fading into dawn. Thank you for staying with me through this long, gentle journey, through Webb's discoveries and the mysteries of the early universe. We've spent 2.5 hours together, moving from observations and science through meaning and contemplation to wonder and rest. I'm grateful you chose to spend this time exploring what Webb found when it looked too deep into space. We've travelled together through many ideas. We explored what the James Webb Space Telescope is and where it operates, learned how looking at distant objects means looking back in time, understood what we expected to find versus what Webb actually discovered. We encountered surprising early galaxies, massive and mature far earlier than predicted, black holes that grew impossibly quickly, mysteries that challenge our models. We thought about dark matter's role, the first stars. Computer simulations tested against reality. We considered whether we might be wrong about the Big Bang, concluding that the framework holds even as details need refinement. We reflected on the scientific process in action, how discovery works, the human side of research. We contemplated what happens next, how these puzzles will be solved through further observation and refined theory. We considered philosophical implications, the beauty of discovery, questions of funding and priority. We found comfort in cosmic perspective, gratitude for light, and rested in wonder. And now, as we reach the end, let's return to the simple truth at the heart of our journey. Webb looked deeper into space than any telescope before it. What it found was shocking, not because it contradicted everything we know, but because it revealed the early universe was more complex than we expected. The answer to what Webb found is this: galaxies that are larger, brighter, and more mature than our models predicted for such early times. Black holes that grew faster than we thought possible. An active, dynamic, surprising early universe that challenges our understanding while confirming the basic Big Bang framework. Probably, these observations will lead to refined models of galaxy formation, better understanding of how stars form in the early universe, improved simulations that match what Webb has seen. The puzzles will be solved. The mysteries will become understood, though new ones will surely emerge. If you enjoyed this slow drift through cosmic mysteries and unexpected discoveries, a like and subscribe helps others find these calm explorations. And if you have thoughts about Webb, about early galaxies, or about the universe's surprises, the comments are a space for sharing. To those already part of this community, thank you for being here, for bringing your curiosity to these explorations. Wherever you are in the world right now, I hope you found some peace in this journey. I hope your breathing has slowed, that the day's concerns have faded to background, that your thoughts have turned to galaxies and light and the vastness that surrounds us. I hope you feel connected to something larger, to cosmic history and human achievement. Look up at the stars if you can see them from where you are, or imagine them if you can't. Among those points of light are galaxies, billions of them, each containing billions of stars. Webb has shown us some from the universe's earliest times, revealing a cosmic dawn more complex than we imagined. All those galaxies are real, existing across vast distances and times, following physical laws, evolving slowly through cosmic eras. Some of the light from them is reaching Earth right now, photons that began their journey billions of years ago, finally arriving at this moment. The mystery of how early galaxies formed so quickly is being investigated by scientists worldwide. The question of how black holes grew so fast is being modelled in simulations. The puzzle of why the universe surprised us is being examined from every angle. But beyond the science is wonder. Wonder at the beauty of the images. Wonder at human capability to build Webb and make these observations. Wonder at the universe's complexity and our ability to understand it. Wonder at being alive in a time when such discoveries are possible. Sleep well tonight. Dream of early galaxies glowing in cosmic darkness, of massive stars forming in the universe's first moments, of black holes growing in ways we don't yet fully understand. Dream of Webb, orbiting silently 1,000,000 miles away, collecting ancient light, revealing cosmic secrets. Dream of the scientists working to solve these puzzles, of the gradual process of discovery, of models being refined and understanding deepening. Dream of future telescopes that will see even farther, revealing even earlier epochs, uncovering even deeper mysteries. Dream peacefully, knowing that the universe is vast and strange and beautiful, that we're part of it, connected through matter and energy and time. Dream knowing that wonder is always available, that mystery enriches rather than threatens, that not knowing everything is part of the human experience. Good night. Rest in the cosmic vastness, in the light from ancient galaxies, in the wonder of discovery and the comfort of not needing to understand everything. Sleep well, and when you wake, the universe will still be here, still mysterious, still inviting exploration, still worthy of wonder. Good night.